Wow, what a bright day.
Yeah, it's always shining in California. Perfect for solar cells.
Yeah, do you know that some of the buildings here on campus have solar cells on the roof?
Really? It's good to know Stanford's using some renewable energy.
Yep. Also, did you know that California is the top state in solar PV capacity?
Huh, what's PV?
Oh, PV stands for photovoltaic. Solar PV is a device that converts sunlight energy directly into electricity.
You mean like one of those metallic strips on the calculators that run without batteries?
Exactly. And those metallic strips are also used to power watches, buildings, satellites, and many other things in this world.
Wow, that's amazing. We're using the sun's abundant energy to fuel our world.
What's also amazing is that many of these solar cells are made using one of the most abundant elements called silicon.
Like Silicon Valley silicon?
Yeah, silicon is heavily used not only in solar cell industry, but also in microchip and processor industries. That's because silicon is the principal component of semiconductors.
Wow, you know a lot about solar cells. I wonder if others are as knowledgeable as you are. What is solar energy and how do we get it?
Capture energy from the sun. Solar cells.
Solar energy is, oh my gosh, this feels like a test.
These things called photons that you can probably harvest through silicon-derived cells.
Energy that's from the sun's rays shining down on a solar panel.
From this side, you can get many sources of energy.
Usually people use like PV cells and things like that.
Can you use dyes to make solar cells?
I don't know such a technology. I don't know.
I have no idea, so I'll say no.
Different colors reflect different light frequencies, I guess.
There's something in the dye, and they put a layer of it.
Sight electrons off of anything. It's easier to do it off of silicon wafers than a raspberry, I would guess. Fruits seem to use solar energy pretty well, like your plants do, so I don't know. I wouldn't be surprised.
The dye-sensitized solar cell is a class of low-cost solar cells that is made with a thin film of titanium dioxide and a dye you can find from fruits and plants.
These cells are also known as Grätzel cells, named after Swiss professor Michael Grätzel. Dye-sensitized solar cells are extremely inexpensive and can be made with readily available materials. You can make solar cells out of dye?
Yeah.
As in color?
Yep.
How do you do that?
Well, since we're in front of this lab, why don't we go in and see?
Alright.
How to build a dye-sensitized solar cell.
The dye-sensitized solar cell stands out from other technologies because of its low cost and production from readily available materials. We first clean a conductive, transparent glass with soap, acetone, and isopropyl alcohol. In the lab, researchers put the glass in a machine called a sonicator, which applies sound energy to remove any remaining particles such as dust. The glass slide is then placed in a UV ozone oven, which further cures the slide and removes any additional contaminants. We want the glass slide to be as clean as possible before depositing the layer of titanium dioxide. We use a piece of equipment in the laboratory called the doctor plate to deposit the titanium dioxide layer. The glass is secured onto the machine using Scotch tape. Titanium dioxide, which is commonly used in paint and sunscreen, is applied onto the glass slide. You can find titanium dioxide for as low as $12 per pound with a simple search on Google. The doctor blade slowly applies a uniform layer of titanium dioxide onto the glass. This process can be done manually if you do not have access to a doctor blade. Once completed, the glass is then removed from the machine and placed onto a hot plate to completely dry. Our product should be what you see here, a conductive glass with a nice even layer of titanium dioxide. The next step of the experiment is to obtain our dye. We are using Tazo passion fruit tea. Other effective dyes can be extracted from fruits and plants such as blackberries, raspberries, and for the ladies, hibiscus flowers. These dyes contain contain a pigment known as anthocyanins, which has the ability to absorb light and convert it into electrons. It is now time to stain the titanium dioxide layer. We put the glass in a petri dish and pour the dye over it. The titanium dioxide is allowed to soak for approximately 30 minutes. As the titanium soaks in the dye, we combine 0.05 molar iodine with 0.5 molar potassium iodide and water-free ethylene glycol to form the electrolyte solution. Now we must determine which side is the conductive side for the counter electrode. To test this, we use a voltmeter and set its resistance. The non-conductive side will not generate a resistance, while the conductive side will be able to. We coat the conductive side with graphite by using a pencil. The graphite acts like a catalyst that keeps the reaction going. It is now time to assemble the dye-sensitized solar cell. Now that the glass slides have been sitting in the dye for half an hour, we can remove them from the petri dish and rinse them off in isopropyl alcohol. The titanium layer should now turn a rich dark purple color. Using a pipette, apply just a few drops of the electrolyte solutions onto the dye. Take the pencil side of the counter electrode and put it down on top of the cell. Make sure to offset the edges so we could apply the voltmeter probes when testing. Clamp the cell together using binder clips. And there you have it. You've built your own dye-sensitized solar cell. We can now test the voltage of our solar cell. Under the light source, the cell generates approximately 0.4 volts. When removed, the voltage drops noticeably. We're going to demonstrate how the voltage drops when the light is turned off. When a few of these solar cells are connected together, we can potentially generate enough voltage and current to power something as small as an LED. This is a fairly new technology. As more research is done, the efficiency will continue to climb. The dye-sensitized solar cell can offer an eco-friendly and inexpensive source of energy.
A layer of nano titanium dioxide, which is the N-type semiconductor, and then a layer of dye which directly interacts with photons from the sunlight, and then a layer of electrolyte which replenishes electrons, and then electrode, in this case graphite, which is the P-type semiconductor. All of this is sandwiched in between conducting glass plates. At the molecular level, the diagram of layers is very misleading. In actuality, gray titanium dioxide and red dye particles are mixed together. More specifically, nano-titanium oxide particles act as a framework to hold the dye molecules. As sunlight comes down on the solar cell, it passes through the conducting glass plate and hits the layer of dye and titanium dioxide. Photons from the sun's electromagnetic radiation hits dye molecules and excites the electrons. Attaching onto the large surface area of nanoparticles increases the production of electrons. The excited electrons from the dye will transfer through a conducting glass plate and through the wire as electrical current. Meanwhile, electrons from electrolyte will transfer up to those dye molecules that just lost its electron and bring it back to its original state. At the same time, electric current will flow through the wire and power a lamp, motor, or other output devices. And then electrons will flow through the conducting glass plate to the graphite, which will transfer electrons to the electrolyte, returning it to its original state. Then, sunlight hits dye molecules, and the cycle continues.
The advantages of the dye-sensitized solar cell.
The greatest advantage of dye-sensitized solar cells is their low cost. To see why other types of cells are more expensive, we visited a silicon cell manufacturing plant called Cali Solar. The process of making silicon solar cells requires many energy-intensive steps. First, the silicon must be purified to around 99.9999999%. It is then formed into these ingots, which are cut into wafers using incredibly fine threads. Even so, about 40% of the silicon is lost during the cutting process. Each wafer is then processed and coated with an anti-reflective coating. The final result of this process is a cell that will take 4 years to generate the amount of energy that went into making it. Commercial manufacture of dye-sensitized solar cells is more complex and more highly mechanized than our demonstration. However, it is far less energy intensive and far cheaper than the manufacture of traditional silicon cells. According to the International Center for Theoretical Physics, dye-sensitized solar cells are 5 times cheaper than traditional silicon cells when used as building integrated photovoltaics. Dye-sensitized cells also have a number of other benefits. They are lightweight, flexible, and durable, making them practical for things like backpacking. They are also better than traditional silicon cells at absorbing diffuse solar radiation. As you can see from this graph, dye-sensitized solar cells outperform silicon cells with the same nameplate capacity. Dye-sensitized solar cells are not yet a panacea. They are not that efficient and are limited by the properties of their liquid electrolytes. But research like that of Yikong Ding is tackling both of these issues, creating solid-state dye-sensitized cells with greater efficiency. There are very promising applications for these cells.
It can be made with different color, which is important for some application. Because imagine if you have so some Japanese companies are commercializing building integrated photovoltaics. So it's basically, you can think of dye cells as the color is determined by the dye you use, and changing the dye will give you a different color. So therefore, they can make really, really pretty stuff with dye-sensitized solar cells, and that's useful for some application. For example, you can have, like, say, a window that has your company logo on them from the dye-sensitized solar cell.
Not only can dye-sensitized cells serve as windows, but they are also being integrated into all aspects of buildings. There's even efforts to create dye-sensitized paint. Given the low cost of these cells and all the research going into improving them, it may not be long before they become a major player in the solar energy industry. We may soon find dye-sensitized cells incorporated seamlessly into the buildings all around us.